Okay, it's 5:30, so I guess we can start. Any questions you have? So, yes?
I have a question about the homework,
Okay.
about what you mean by lines of action. Are those all the lines that are coming out of the surface, or the resultant vectors that are coming out of each surface?
The resultant vector. Line of action of a force is the same as the direction of the force.
So that has nothing to do with the magnitude?
Yeah, line of action has nothing to do with the magnitude, right?
Okay.
Which problem? Notes?
It's the very last sentence in the first problem.
Oh,
homework
first
8.
problem.
Yeah.
The first problem says find F in order that the body is in equilibrium with zero body force and the surface traction on the plane are given by this. There is no line of action here. It's a different one. Which one is it?
That was the first one. It says indicate on this homework.
This is this is a different assignment. Okay. Okay. It says you have the line of action is the same thing as the direction of the force.
So do you want just one vector coming out of each face, or?
Well, see, on each plane you will have three vectors.
You'll have what?
On each plane you will have three vectors.
Those are the traction.
Pardon me? Those are the tractions.
And then the resultant is just one line.
Right.
Yeah.
So the resultant of those three forces, that's what I want you to show.
Okay.
I mean, if you have difficulty in plotting a 3D sketch, I think it should not be that hard though, to plot a 3D sketch.
Draw a line.
Can't you just draw like an arrow? I mean, it's a simple.
It's a simple vector.
Yeah.
So I don't think it should be any big problem.
Okay. I just want to make sure that you weren't looking for like a vector field or something like that.
There is no field. There is only it says resultant force. So it doesn't. Field means it is distributed over the body. What it says is find the resultant force on a plane and show that force. The whole idea is for you to appreciate that the force does not always act along the normal to the surface. So you have both normal stresses as well as tangential or shear stresses.
Okay. Yeah, that clears it up.
Okay, anything else on your minds? So I guess many of you, not many, of course you are here, many people went to the game, I guess. Well, it's okay. So what we are going to do now is study the next balance law. Oh, you cannot see us. Wait a minute. Classroom. Stuck. Oh. Now you can see it. Oh, sorry. Thank you. So we studied balance of mass, balance of linear momentum, balance of momentum, and the next one is balance of energy. It's not in the same sequence as in the book. It's partly because this one is similar to the other balance laws. So those people who are not here, they should be able to follow without too much difficulty. Yeah. So that's the reason I'm skipping. Like I'm not going as it is, as the material is in the book. So we'll look in the present configuration. Again, take a small piece, even though the one I'm showing is not small. So this is part P. And we want to write the balance of energy. So what kind of energy can the material in this part have? We are writing balance of energy. is a scalar quantity. It has no direction. It just has magnitude. I see Katie smiling, and I see her neighbor smiling. So what kind of energy can it have? Yes.
It can have potential energy and kinetic energy and maybe chemical energy, but probably not.
We are not considering chemical reactions, so chemical energy is out. Potential energy is because of the position of the particle or the body relative to the, say, center of the Earth. Let's assume we are on the surface of the Earth. So we are not taking the body from ground up. That really does not involve much deformation. So that part is out.
Thermal energy?
Good. Thermal energy, very good, yes. So if you heat the body, then it can have thermal energy. Also, what happens to a spring? If you stretch a spring and hold it there, say I take a spring and stretch it. Can I lift a weight with it? The answer is yes or no. Supposing I stretch the spring and somehow I have a mechanism to put a weight at the bottom. And if I let the spring go, will the weight go up or not? Yeah, it will go up. It's similar to what potential energy you were saying, except that I'm talking about a spring now, and since I stretch the spring, I have deformed it. So there is some internal energy stored in the body, either because of the temperature change and it could be both of them. It could be both temperature change as well as deforming the body. Okay, so there's internal energy stored in the body. Like in our case, of course, in the human body, most of the time the internal energy stored is because of the food we eat, and that's the chemical reaction. The food is converted into sugar and whatever, and then it's the chemical energy which we are using, which I'm using to talk to you, or I used in walking from Norris Hall to Burroughs Hall. So we are not considering the chemical energy. We are only going to consider energy due to deformation as well as temperature change. So let's assume that part is, and that's measured per unit mass. So if E is the energy per unit mass, we multiply it by the mass of the piece, and then we integrate it. What else? What other kind of energy the body can have besides potential, which we said we will not consider, because potential energy is relative to the location of the body with respect to Earth. I think you want to say something. Kinetic energy. Kinetic energy. So whenever something is moving, there is energy associated with it. And different particles of the body are not necessarily moving with the same speed. So the kinetic energy is mass, 1/2 mass velocity square, and velocity square is vi. So that's vx square plus vy square plus vz square. So that's the rate of change of energy. Now this should equal what? It's not chemical energy. Okay, there is no chemical reaction. We are not considering chemical reaction. Since it is balance of energy or conservation of energy, I mean, this is how things are changing. So something has to balance it. So what is supplying energy to the body? Heat. Good. What? Yes? Working of forces. See, if there are forces acting on the body, they may be doing work on it. So what kind of forces did we consider, or what kind of forces are we considering in this course? And when I say in this course, actually it's really not only in this course, this is what you have been doing forever, for the last 4 years or so. So it's not only this course. So what kind of forces are we have we been considering? Surface and body forces. No, this is the working. Working. When you say ing at the end, that means rate. Work is force dotted with the displacement. Working, ing at the end, is rate of work done by forces, so that will be force dotted with the velocity. So we have a contact force dotted with the velocity of the point of action of that force. So that's on the boundaries, plus we have body force times the, like, dotted with the velocity of the particles. And now one of you very correctly said heat. Actually, two of you said heat. One from Wake Forest and one from this room. So heat. Now, how can the body be receiving thermal energy? How can body be receiving thermal energy? See, today was a sunny day. How many of you walked in the sun? Did any one of you walk in the sun? You did? Did you feel any warmth? But you were not touching the sun. So you received thermal energy because of radiation. Right? So you received thermal energy because of radiation, and that we will measure per unit mass. So that's plus rho r dV. So r is the energy received from bodies that are not touching us per unit mass. R is really the rate of energy received. It is not the energy. It's rate of energy received. Everything is a rate here. Because on the left hand side we have a rate of change of energy. What else?
Convection.
Convection will come in the boundary conditions. How many of you have cooked anything? How many of you have boiled water in a kettle? None? Come on. You don't make coffee or tea or anything? I mean, boil something, spaghetti or noodles? So you do, right? And how many of you touch the pot by mistake without the pot holder? None of you did. You guys are very smart. So if you touch a hot pot, what happens to you? You feel the heat. So the heat is being transferred to you because the pot is hotter than your body. So that's the contact part. Okay. So this unshaded portion is exchanging heat with the shaded portion through the common interface. The unshaded portion of this body I showed you, or I'm showing here, is exchanging heat with the shaded portion through the contact surface, through this common interface. And that we measure per unit area. Like we had a contact force, we have a contact heat, or contact source of energy. We had a body force, we have a body source of energy. So it's analogous, it's the same, similar. So plus then H dA. So this H is the rate of energy received per unit surface area. this H is the rate of energy received per unit surface area. Okay, now let's see how many of you remember Koshi's postulate. So what did Koshi say about the dependence of F upon the orientation of the surface? What did Koshi say about the dependence of the surface tractions upon the orientation of the surface? And what did Koshi assume? I need to fill in the next line. Yes, yes.
It only depends on the point of action and the normal. To the
Only
surface.
depends upon the outward normal. So the surface tractions depend upon the orientation of the surface only through the outward normal. The analog of that is this rate of contact energy, the thermal energy we are saying, H. It depends upon the orientation of the surface only through the outward normal. So this H, the rate of energy received through the common interface, depends upon the orientation of the interface only through the outward normal. So this is the analog of that. Then what did we do? We said, okay, this balance of linear momentum holds for a pillbox, and the balance of linear momentum holds for a tetrahedron, and we showed that F is a linear function of n. Right? So if we follow the same reasoning, and to make life simple, you can assume that the body is rigid. Well, we can say the body is at rest, not rigid. The body is at rest. So then, like Carrie from Wake Forest said, we basically are dealing with thermal energy. The body at rest can be deforming too, but let's assume that the body is at rest, so there is no kinetic energy associated with it. And then we can say d over dt of rho e dv part p. Since the body is at rest, there is no working of the forces. So this will equal then rho r dv plus HdA. And now if you use the argument that this balance of energy holds for a pillbox, remember we use the mean value theorem, so use the same argument. For a pillbox, we will get that Hx, if you change the direction of the normal, then you change the sign. If you change the direction of the normal, then you change the sign of H. So if you apply this balance of energy for a body at rest to a pillbox, you will get this relation. If you apply this to a tetrahedron, then we will get that H is a linear function of n. And the argument, the reasoning is exactly the same, so I'm not going to repeat it. It's exactly the same as we did for a balance of linear momentum. I hope some of you remember it, yes? You want to ask something? No. So we use the balance of linear momentum for a pillbox and then for a tetrahedron. So it's the same, exactly same reasoning. So if h is a linear function of n, then we can write it as hxn as minus q I ni. I'm going to rewrite it, where q is a function of x, and of course n also is a function of x. But h is a linear function of n. This minus sign is conventional. This minus sign is conventional. I mean, there is no reason to put minus sign there, but we normally do. I mean, one reason is the following. Our positive n points out of the body. So if q is positive, or not q is positive, q is a vector. I cannot say q is positive. Q is a vector. So if q dot n is positive, that means the body is receiving heat. Actually, I should really say if all of this is positive, then the body is receiving heat. Otherwise, it's giving out heat. So Q has a name and is called heat flux. Q has a name and is called heat flux. How many of you have heard of something called Fourier's law of heat conduction? Katie has. Anybody else? So what does the Fourier law of heat conduction say? Okay, so the Fourier law of heat conduction is a linear relation between heat flux and the temperature gradient. So the reason I brought that up is that you should have come across the term heat flux before in your either thermodynamics class or heat transfer class. And since I brought up the word thermodynamics, this balance of energy is also called first law of thermodynamics. So balance of energy is also called first law of thermodynamics. How many laws are in thermodynamics? How many laws of thermodynamics have you studied? Oh, come on, you must have. How many of you have taken a course in thermodynamics? Okay, you have taken it. Katie, you have taken any course in thermodynamics?
Yes, I have.
What about Francis?
No,
Have you taken a course in thermodynamics?
I haven't.
How many of you have not taken a course in thermodynamics? You have not, because you are a physics major. Okay. And you have not? Oh, you are a civil major. You are a civil major, so you have not. Okay. So for those of you who have taken a course in thermodynamics, how many laws of thermodynamics are there? If there is first, there must be something else. Otherwise, I won't say first law of thermodynamics, right? I told you that the other day too. Like if first Kolakov stress tensor, so there must be second Kolakov stress tensor. 3. Sorry, no. It's between
There are
1 and
2 laws of thermodynamics.
I'm sorry, how much? Vince? Oh, no, sorry.
There are 2 laws.
There are 2. Very good. So there are 2 laws of thermodynamics. Okay? So the first law is balance of energy. What about the second law?
Entropy?
No, it's a you have to say a sentence. Like it's not one word. Sorry, it's not one word. I mean, you have to say a sentence probably is having 7, 8, 10 words.
Well, I mean, I don't remember the exact law, but it deals with how entropy is related to temperature and heat.
Not quite. Sorry.
The
Heat
entropy
cannot.
in a closed system never decreases.
Yeah, never decrease what?
The entropy never decreases in a closed system.
Yeah, that's close enough. So actually, heat cannot flow from a body at a lower temperature to a body at a higher temperature without doing some work on the body. That is one statement. This is not, see, that's where the problems come up. In the second law of thermodynamics, there is no unique statement. Like Kunz gave one, and I'm giving one. But if you walk out of the room and go to mechanical engineering and talk to a professor of thermodynamics, he probably will give you, or she probably will give you, a different definition. Okay? So, anyway. First law of thermodynamics is uniquely defined. So there is no ifs or buts, or there is no confusion between in the definition of the first law of thermodynamics. Okay, so heat flux. So those of you who have heard the Fourier's law of heat conduction is Qi equals minus K delta theta over delta Xi, where K is called thermal conductivity, and T is the temperature change. K is called thermal conductivity and T is the temperature change. Also, since I was going to say for a rigid body, but let me wait for a while. Okay, so now we know what is H, like it's minus Qi and I. So we are going to substitute for H in this our balance of energy. Also we learned that d over dt, this quantity, I can take it inside the integral and it will be E dot and it will be time derivative of this. Okay, we proved that a week ago, or actually maybe a little more than a week ago, that if you have a d over dt of rho phi dv on part P, this is equal to rho phi dot dv, part P. So we are using that result now. Phi equals E here, and phi equals vi here. Okay. Also, what is Fi equal to in terms of stresses? Koshi stress. In terms of the Koshi stress tensor, what is Fi equal to? I mean, we proved that a couple of days ago. Tij and J. So let's substitute that. Also, this H is minus Qi. We just said that. So I have made a few changes indicated by red color on the previous equation, and I'm afraid you, of course, don't have a red pen, so you cannot do it. So you are basically rewriting it. So I will wait for a few seconds. Is it making sense what I'm saying? Okay, so on the left hand side we have done rho E dot plus rho over 2. If we differentiate this, we get Vi dot Vi plus Vi dot, the chain rule of calculus. And all of this is integrated over the volume. So this equals, we have here now Tij, Vi, Nj. This term is Tij, Vi, Nj. And can we use the divergence theorem now? Because see, J and J is summed. So we can use the divergence theorem. And if we use the divergence theorem, we will get Vi, Tij. This whole thing is differentiated with respect to Xj. This whole thing is differentiated with respect to Xj, and we get dV here. So now it's on the volume. Plus, the next term we don't do anything. Rho Bi, Vi, dV. The next term we don't do anything. So we just say rho and the next term is minus Qi Ni on the surface, like it's a surface integration of Qi Ni. So is who's at Wake Forest? Is it Carrie and I see two of you there, right?
Here.
I'm sorry, all of you are there?
Carrie is not here.
The rest
Okay.
of us are here, but Carrie's not here.
Okay, so will one of you tell me how can I use the divergence theorem on this term? See, we have Qi and I. We want to simplify this. We want to change that to the volume integration. So if we use the divergence theorem, that will do it. So what will we get if we use the divergence theorem? Am I making sense? The answer, I'm sorry?
None of us here know it.
Oh, okay. Well, see, it's the same thing as we did here. So it's Qi, comma I, like divergence of Q. And this is on the volume. So it's Qi comma I, or delta Qi over delta Xi, or divergence of Q. That's why the name divergence theorem, because this is divergence of Q, or this is divergence of a vector. Now every integral is on the part P. It's a volume integration, all of them. All of the integrals are on the volume. So we can combine them. So what if we combine them? So we will get something like G of dV on part P should be 0. But I did not give you the value of G because it's a combination of all these terms. If we combine all of these terms, all of them are integration over the part P, volume integration. So we can combine them. And if this equation has to hold for every part P, then G must be 0. Okay, so this is true only if G is 0. So let's set that G equal to 0. So we get rho E dot plus, these two terms are same, Vi dot, Vi, they are the same terms. So we can add these two up, and that will take care of this 2. So we have rho E dot, then rho Vi, Vi dot. That's from this first term. Equals Vi Ti j comma j plus rho Bi Vi plus rho R minus Qi comma I. Is it okay? So we have copied all of the terms. Please speak up if there is any doubt, because we are almost done with this simplification. Except, let's look at this term now. Vi Tij comma j. This is differentiation with respect to xj, little xj. Chain rule of calculus. Chain rule of calculus. So that means I should have delta Vi over delta xj Tij plus Vi delta Tij over delta xj. This is product of two functions, so I will get two terms. Yes?
Is this the first instance where comma j is differentiating with respect to little xj as opposed to big xj?
No. No. With respect to big X, we have been denoting by like uppercase index. If we are differentiating something with respect to big X, then we write comma uppercase index. So the lowercase index means we are differentiating with respect to little x. Uppercase index means we are differentiating with respect to big X. Okay. So let's simplify this term. So we can write delta Vi over delta Xj as 1/2 delta Vi over delta Xj plus delta Vj over delta Xi plus 1/2 delta Vi over delta Xj minus delta Vj over delta Xi. So what we have done is we have added this and subtracted that. So we wrote 1 equal to 1/2 plus 1/2, and then we added this and subtracted the same thing. So we are okay, balanced. Of course, there's a purpose behind it. What is this thing equal to? D. Very good. So this is Dij. And what is this one? Wij. So that's the spin. And W is skew symmetric and D is symmetric. Therefore, delta Vi over delta Xj Tij equals Dij plus Wij Tij. No, we are not missing any half. With the half, this is Dij. No, we are not missing half. Both terms are with the halves. So this is equal to Dij Tij plus Wij Tij. And now someone is going to tell me what is this term equal to. Very good, 0. So that was one of the homework problems. W is skew symmetric, T is symmetric. So if you expand these 9 terms, 3 of them identically 0 because W11, W22, W33 is 0. The remaining 6 terms, they cancel with each other. So this thing is 0. Now Tij, Dij, this equals, what is Tij? What is the name for it? Yes, Francis?
True stress tensor.
True stress tensor. Good. Koshi stress tensor or true stress tensor. So this equals working, which means rate of doing work of internal stresses. So this is the and this is per unit present volume. Per unit present volume. So this is the working, that means rate of work done of internal stresses, those stresses which are induced in the body. You cannot see them. There is no way you can see those stresses. But they are there. So if you have deformed the body, the stresses are there. If you apply loads to it, stresses are there. Even though I said the word deform, okay, so to clarify myself, supposing I take this piece, this is a cylinder, and let's assume this is made of rigid body. Of course, as we know, there is no such thing as rigid body, but let's assume it's rigid. So I apply a 100 Newton force, and let's assume the area of cross section of this thing is 1 millimeter square. And the body is rigid. Is there any stress induced in the body? Tim?
Yes.
So what is that?
100 kilopascals.
So 100 newtons per millimeter square. Now I'm not going to translate that into kilopascals because I may make a mistake. It's probably more than that. But then it's 100 newtons per millimeter square. It's 100 newton per millimeter square. Good. And there is only one component of stress because of this loading. What is the strain in the body? What is the strain induced in the body? Yes. What is the strain induced in it?
I would say 0.
Zero. Because the body is rigid. So there can be a stress even though the strain is 0. Okay? The stress has nothing to do with whether there was strain induced in it or not. The stress has something to do with the loads applied. Okay, so now let's complete our story. And then, okay, now remember this thing is this term. So this term is equal to Dij Tij. That's what we showed. This term is Dij Tij, and let's go back to our equation, the one we have this term, so I'm going to substitute for I'm going to substitute for this term these two. So let's write rho E dot, and let me take the other term to the left hand, to the right hand side. So I have, and I'm going to take Vi as a common factor. So I have minus rho Vi dot. That is this term. I took Vi as a Vi outside, so I will get minus rho Vi dot. And this term we just saw, I guess you can see it. This term is the sum of these two, right? This has a Vi in it, which I took it outside, so I'm going to write that as delta Tij over delta Xj. And the other term is Tij Dij. This is equal to these two terms, so I copied them here. This one has a Vi in it, so I'm going to write that here. And what we are left with is then plus rho R minus Qi comma I. We are almost done. Now, who will tell me what is the term in this brackets? Or very good, it's 0. Why? This balance of linear momentum. So the balance of linear momentum requires that this term must be 0. And remember, that balance of linear momentum must hold. Every continuous body must obey the balance of linear momentum. So we can simplify our balance of energy. So what we get then is the following. Rho E dot equals Tij Dij plus rho R minus Qi comma I. And this one is called balance of internal energy. So this one is called balance of internal energy. Instead of saying balance of energy, this is balance of internal energy. So maybe I should write down. So this is balance of internal energy. Tij Dij is the working of internal stresses. And please tell me if the connection gets cut off, because it's almost 20 after 6. I think they are supposed to keep it for.
I think we'll be okay.
Okay, good. So just one more line, maybe 2-3 more minutes, and then we will be done. Let's assume the body is rigid. Let's assume that the body is rigid. So what is Dij for a rigid body? What is the strain rate tensor for a rigid body? Can a rigid body deform? No. So the strain rate tensor for a rigid body is 0. Therefore, even though there are stresses in the rigid body, but there is no strain rate, there is no strain. So the working of internal stresses is 0. So we get rho E dot equal to rho R minus Qi comma I. Now how can the internal energy of rigid body change? Actually, one of you at Wake Forest already answered that question. The internal energy of rigid body can change because of change of temperature. Internal energy of any body can change because of change in temperature, but internal energy of rigid body can change only because of change in temperature. So E, if we take a simple constitutive equation, E equals C theta, or theta minus theta 0, where theta 0 is the reference temperature. And what is C called? Maybe let me write the next line, maybe then you will know it. So if I substitute in here, I get rho C theta dot equals rho R, and let's substitute the Fourier's law of heat conduction. Let's substitute the Fourier's law of heat conduction. And if K is a constant, so K comes out, so this thing is delta square theta over delta xi plus rho R. And after we give the meanings of C and K, we will quit. K is a constant, like we are assuming the body is homogeneous. We are assuming the body is made of the same material. So K is a constant. K does not depend upon x, little x. So what is the meaning of C? This little c you see here, well, before we go that far, has any one of you seen this equation before? Did any one of you take a heat conduction class? I heard the word convection, so if you know thermal convection, so you must have taken a heat conduction course. No, you did not take a heat conduction course. Anybody has studied heat conduction in a body, in a body? Any one of you has studied heat conduction. So what is this equation? This is the equation you use to study heat conduction.
Diffusion equation?
Yes, you can say it's a diffusion equation, because this is a diffusive term. So this is a heat conduction equation, or this is heat conduction in a solid, and if you have a fluid, then theta dot will be different, but since I took the body to be rigid, I should not really say a fluid. A solid is more like a rigid body than a fluid is. Or you are neglecting the deformations of the body. So C is called specific heat. I assume you probably have come across the word specific heat. So this C is called specific heat. And what about K? K? K is thermal conductivity. I mean, it's without the word coefficient. So K is thermal conductivity. So this K is thermal conductivity. The reason I simplified or reduced to this form is I thought, of course I was wrong, that you might have seen this equation before. So whatever you have studied before does follow from what we have been doing. Yes?
Fine. We need to keep it or just get rid of it?
Oh, no, sorry. There was a minus here. Because Qi was minus K theta comma I. Yeah, you are right. I goofed. So my mind was going faster than my hand was. So there's a minus sign here because Q is minus K theta comma I. Okay, well, thank you. For the Wake Forest people, can you still hear me?
Yes.
My secretary, Norma, is on vacation, and that's why you have not received your homework yet.
Okay.
So she
Thank
will
you.
be back on Tuesday. Then I will email the PDF file to you.
Okay, thanks.
Yeah, you are welcome, and please tell others to.